Fetch robot object detection and manipulation. This presentation will showcase steps made towards manipulation of objects in 3D using Fetch Robot's built-in depth camera and 7-joint robotic arm. This will include simulation setup using ROS-Pi, control of robotic arm, resolve motion rate control, image data processing, object recognition, addressing challenges in coordinate frame transitions. We'll also explore YOLO V8 and its potential use for visual servoing. Let's dive in. The simulator was set up as per instructions in the Fetch Robotics documentation. ROS-Pi was used to interface with topics and services for control of the robotic arm and receiving live image data and joint configurations. Python 3.8 was set up alongside the default Python 2.7. 3.8 was planned to use for its integration with YOLO V8 and object localization. When facing compatibility issues with ROS Melodic, Python 2.7 was used to forward data in JSON format to the Python 3.8 script. Arm control. The arm is controlled by publishing trajectories to the topic shown below. See the example script that constructs messages to be sent on this topic. A list of joint names found in the documentation are associated with desired joint angles. A time in which the joint state should change from the current state to the desired state is also entered. A similar method was used for control of the joints associated with directing the head camera. Resolve motion rate control. A method for control of end effector velocity and angular velocity was developed using built-in robotics toolbox features. This control method may be used in a feedback control system in combination with sensor data to position the end effector relative to detected objects as needed. Receiving and interpreting image data. To address compatibility issues between ROS Melodic and Python 3.8, a Python 2.7 script was developed to relay crucial data to the main script. This script runs on a separate thread initiated from the main Python script prior to entering the main loop. Depth image data and TF information are encapsulated as JSONs and transmitted over newly established topics. Using OpenCV, the depth image is scaled, normalizing all values from 0 to 255. The jet color map is applied for visualization alongside the RGB image. Basic object recognition and 3D localization were demonstrated using a single Reb cube. The cube's location relative to the depth camera is calculated by extracting the central pixel within the bounding box and considering its X and Y values in the image and the depth value associated with that pixel in the depth data. These calculations were based on the pinhole camera model assumptions. The camera intrinsic parameters were made available via ROS topic. Objects were successfully localized within the camera coordinate frame, as can be seen. However, issues were faced when attempting to transfer these points to the base link frame or to the global coordinate frame. These issues prevented attempts at visual servoing. Despite this, a visual servoing method will be discussed later in the video. YOLO V8 object recognition. CUDA was set up to work with Python 3.8 and PyTorch. YOLO V8S, one of the latest PyTorch models released by Ultralytics earlier this year, was tested for feasibility in object detection. The script shown takes in live images from my computer's built-in webcam and draws bounding boxes around the detected objects. This script may be adapted to run object detection on RGB information received from the Fetch robot. The 2D bounding boxes may be used in combination with depth information provided natively by the Fetch bot to localize arbitrary objects in 3D space. Due to issues faced when loading 3D models into Gazebo, this was not attempted. Visual servoing. A method for visual servoing may be possible with everyday objects using YOLO V8. Object localization using the depth camera information was demonstrated with the red cube. The same can be done with YOLO V8 bounding boxes. By selecting key pixels within the bounding boxes generated by YOLO V8, the 3D location of arbitrary objects may be determined. This information can be used in an RMRC-based feedback controller where the velocity of the end effector is proportional to the error between the end effector's current location and the object's detected location, with velocity capping for safety. This would allow for the positioning of the end effector arbitrarily with respect to the objects desired to be picked up. Conclusion. Although in the end visual servoing was not successfully attempted, progress in object detection and object localization in 3D using depth camera information has been demonstrated. Further experiments may be run with similar systems in the future to explore the feasibility of visual servoing in the manner described. Thank you for taking the time to listen to this presentation. All feedback is highly appreciated.